Hello all. We will discuss in this lecture Introduction to AC Circuits. We will begin by AC concepts, then the phase relations, then the average value. After that, we will see the effective value and the RMS value, or the RMS value. They have the same meaning. Then the response of basic elements R, L, and C to a sinusoidal voltage or current. Then the reactance and impedance. First, we will see the definition of alternating quantities. An alternating quantity, it changes continuously in magnitude and alters its direction at regular intervals of time. We have three forms or main forms of the alternating quantities: the sinusoidal, which is a sine or cosine wave, the voltage with respect to time, and the second is the square wave, also the voltage with respect to time. We have positive half cycle and negative half cycle. The third shape is the triangular wave, also voltage or current with respect to time. Half cycle is positive and the other half cycle is negative. Important definitions. First one is the amplitude, which is the maximum value in positive or negative attained by an alternating quantity or reached by an alternating quantity, and is called also the peak value. Periodic time or time period. It is the time taken in seconds required to complete one cycle of alternating quantity. It is the time of one complete cycle for a sine wave. This is the periodic time. The time for a complete cycle for the voltage over time or current, with respect to time. Third, the instantaneous value. The instantaneous value, it is the value of alternating quantity at any instant of time. The instantaneous value denotes by small letter. We denote the instantaneous value by small letter for current or voltage. The frequency, it is the number of cycles that occur in 1 second. The time for frequency, or the unit of frequency, is hertz or cycles per second. The relationship between frequency and time, period of time, is defined by the time taken to complete f cycles equal 1 second. Then the time taken to complete one cycle is equals 1 over frequency, or the periodic time equals 1 over the frequency. The frequency, it is the number of complete cycles by the waveform in 1 second. The fifth term or definition is angular frequency, omega. The angular frequency is defined as the number of radians covered in 1 second. The angle covered in 1 second in radians. The angle covered by rotating coil, or the angle covered by rotating coil. The unit of angular frequency is radians per second, where omega equals 2 times pi times f. This is measured in radians per second, or the speed or the angle covered by the waveform in 1 second, or the angle covered by the rotating coil in 1 second. A cycle, it is a portion of waveform contained in one periodic time. This is a complete cycle, is the waveform, the wave completed in one period of time. We have T1, T2, and T3. All are cycles and all of different beginning. All are bounded by one period of time, therefore they satisfy the definition of a cycle. All of these are cycles as they are contained in a time equals to the periodic time. T1 is a periodic time, T2 is a periodic time, and T3 also is a periodic time. We have the frequency equals to 1 over periodic time measured in hertz, or the periodic time equals 1 over frequency, and T is the periodic time in seconds. We have 1 hertz equals 1 cycle per second. For the periodic time equals 1 second, we have one cycle of the waveform. For 1 second in the second figure, we have 2.5 waveforms. Then the periodic time will be equal to 0.4 seconds. As we have completed 2.5 cycles in 1 second, then 1 divided by 2.5, we get the periodic time equals 0.4. 1 divided 2.5 cycles per second. Here, for the third curve, we have in 1 second, we have completed 2 cycles, then the frequency equals 1 over 2, which is equal, the periodic time equals 1 over 2, then the periodic time will be equal to half. We have the periodic time equals 1 over half. We have 2 cycles in 1 second. Then the periodic time equals 1 over half, or 0.5 seconds. We can convert for the phasor relation angle in radians equals the angle in decrease times the pi over 180. We need to convert an angle in degrees to an angle in radians. Then we multiply the angle in degrees by pi over 180. For an angle in radians, we multiply it by 180 divided by pi to get the equivalent in degrees. We have omega, which is the angular speed, or the angle covered in 1 second, equals the angle divided by time. For a complete cycle, we have the angle equals 2 pi, and the time for one cycle equals t capital, periodic time. 1 over t capital is equal to frequency, then omega equals 2 pi times the frequency. We have the waveform here having a value of a maximum sine theta, and at theta equals 0. This is the time for theta equals 0, and we have this value at theta equals 0. Then there is a phase shift for the waveform to the left by an angle theta, as it begins at negative theta, and the end will be shifted by the same theta equals 2 pi minus theta. The waveform will be a maximum sine omega t plus theta, as we have a shift to the left. And for the curve here, we have at theta equals 0, the value of the waveform equals negative a maximum sine theta, where we have shifted the waveform to the right by an angle theta, and this will shift all the rest of the angles by an angle theta. Pi will be pi plus theta, and 2 pi will be equal to pi plus theta. Then the waveform will be a maximum sine omega t minus theta, as it is a shift to the right. If we have two waveforms, the waveform for the voltage and waveform of the current, here we have the waveform of the current begins at negative 70 degrees, and for the voltage, it begins at negative 30 degrees. If we take the difference between these two angles, then we will see that I leads V by 40 degrees, or the waveform of the current comes before the voltage by 40 degrees, or the voltage lags I by 40 degrees, or the voltage comes after the current by 40 degrees. For the waveforms here, we have the current beginning at an angle of negative 60, and the voltage begins at angle positive 20. Then we have a phase shift between these two waveforms equals 20 minus 60, which is equal to 80 degrees. Then the waveform of the current leads the voltage by 80 degrees, or the voltage lags the current by 80 degrees. For the conversion between sine and cosine, if we have sine omega t plus 90, or in radians sine omega t plus pi over 2, this is equal to cosine omega t. And for sine omega t is equal to cosine omega t minus 90 in degrees, or cosine omega t minus pi over 2. the sine of a negative angle equals negative negative times the sine of the same angle without sine, and cosine of a negative angle equals cosine of the same angle without the negative sign. The average value. If we have a pile of sand with a height changing with this curve for a distance known, we can get the average, or we can make the sand pile with an average height having the same area under the curve above in the same distance. This is the average height or the average value. If we have a bigger distance for the same waveform or the same pile of sand, then the average value will be lower, as we get an average value along the same distance, which is bigger than the distance in the first curve. We can get the average value by dividing the algebraic sum of areas under curve divided by the length of the curve or the period of the curve. Here we have a waveform, maximum positive 14 volt, and the maximum negative is negative 6 volt. The periodic time is equal to 2 milliseconds. This is the time of one complete cycle. We can get the average by taking the areas under the curve, the sum of the areas. We have the first area, which is 14 times 1 millisecond, and the second area, which is equal to negative 6 times 1 millisecond. We take the area with a sign and divide this by the length of the curve, which is the periodic time, which is equal to 2 milliseconds. Then we have 14 minus 6 divided by 2 equals 8 divided by 2, or 4 voltage. Then we can approximate this to a line equals to 4 voltage. This is the average value along the periodic time of the waveform for the same length of the curve. For a complete cycle of sine or cosine wave, we get the average value by taking the integration. The integration is equivalent to the area under curve. For getting the area, we can take the integration. We integrate from 0 to pi a maximum sine theta d theta, or a maximum sine alpha d alpha. The integration of sine alpha d alpha equals negative cosine alpha. We substitute by the two limits of the integration, 0 and pi. We can substitute by the lower limit minus the upper limit, as we have negative cosine. Then we have a maximum cosine 0 minus cosine pi. Cosine 0 equals 1 and cosine pi equals negative 1. Then we have negative 1 equals plus 1, 1 plus 1 equals 2. Then we have the area equals to a maximum. We have the area positive equals to a maximum, and the area negative equals to a maximum with the negative sign, and divide by the length of the curve, which is 2 pi, the periodic time. Then the average area equals 0, or we having the positive area equals to the negative area. Then the average value of the sine or cosine wave equals 0. Now we will see another term, which is called the effective value or root mean squared value. Both AC source and AC source deliver the same power to the load. The positive or negative portion of the sinusoidal AC current power is being delivered at each instant of time to the resistor. The positive and negative portions of the sinusoidal AC voltage or current is delivering power to the resistance at every instant of time. We get the power in AC equals I square R. Then we square I maximum square, and for the sine square we substituted by the double angle theory, which is half 1 times 1 minus cosine 2 omega t. Then we will multiply I maximum square inside the bracket. We get I maximum square times R over 2 minus I maximum square times R over 2 times cosine 2 omega t. We have resistance in a basin with a thermometer, and we have two sources, an AC generator or AC source with a switch S2 and a DC source with a switch S1. We need to find the equivalent DC value or DC source value to the AC source, giving the same heating effect in the resistance or the same power loss in the resistance. The power in AC equal IAC squared times R, as we obtained it here, I maximum sine omega t square times R, I maximum square sine square omega t times R, as we substituted in the below. For the average value, we only have the average value for the first part without the cosine, and the average for a cosine wave equals to 0. Then the PAC average equals I maximum square times R over 2. The average power delivered by the AC source is just the first term, as we said in the previous slide, since the average value of a cosine wave is equal to 0. Even if it has twice the frequency of the original waveform, as it having an angle equals to omega t, equating the average power delivered by the AC generator to the delivered by the DC source. Then we have the power AC average equals the power DC. For the power DC, IDC squared times R equals I maximum square times R over 2. We cancel R with R, then IDC squared equal I maximum squared over 2, or IDC equal I maximum divided by root 2, or 0.707 I maximum, which is the effective value or the root mean squared value for the AC quantity. The equivalent DC value of a sinusoidal current or voltage is 1 over root 2, or 0.707 of its peak value, which is the maximum value. The equivalent DC value is called the root mean squared value, or the effective value of a sinusoidal quantity. We can get, as a general form, the root mean squared value of the current equals the root of the mean 1 divided by the periodic time, the mean of the squared. We give the mean of a squared value of the current, we get I square of t dt, and get the area by taking the integration from 0 to t. Or if we can get the area, we get the area under I square of t and divided by the periodic time, and take this then the root of the mean of the squared of the waveform. The relation between the peak value and the RMS value is the same for voltages, where IRMS equals I maximum over root 2, or 0.707 I maximum. Also for the voltage, ERMS equals E maximum over root 2, or 0.707 E maximum. Example, find the RMS value of the following waveform. First of all, we get the V square. We square the waveform, 3 squared equal 9, from 0 to 4, and negative 1 squared equal 1, from 4 to 8. Then we get the areas. The area equals, the first area equals 9 times 4, and the second area equals 1 times also 4, which is 8 minus 4, negative 1 squared, or 1 times 4, and then divide by the period or the periodic time of the curve, which is 8, and then we take the root. Then it will be the root of 36 plus 4, which is equal to 40, divided by 8, which is equal to root 5, equal 2.24 voltage. Determine the average and RMS values of the following waveform. First, we get the RMS value. We square 40 from 0 to 10, which is equal 1600, and we square negative 40 from 10 to 20. We get also 1600 from 10 to 20 milliseconds. Then we get the area. We can divide the area into two areas, or we can get one area. The first area is 1600 times 10 millisecond or 10 times 10 power negative 3, and the second area is 1600 times also 10 millisecond, 10 times 10 power negative 3. Then we divide by the periodic time, which is 20 millisecond, 20 times 10 power negative 3. Then we take the root. Then it will be the root of 3200 times 10 power negative 3 divided by 20 times 10 power negative 3. We cancel 10 power negative 3 with 10 power negative 3 and 0 with 0. We get 3200 divided by 2, or root 1600, which is equal to 40. For the average value, it will be equal to 0, as the positive area equals to the negative area. Now we will see the response of basic R, L, and C elements to a sinusoidal voltage or current. For the resistance, the current in a resistance equals to the voltage across the resistance divided by the resistance from Ohm's law. V across the resistance equals V maximum sine omega t divided by R. We get V maximum over R, which is equal to I maximum, times sine omega t. For I maximum is equal to V maximum over R, where R equal V maximum divided by I maximum. The voltage and the current waveforms are having the same angle, then they are in phase. V maximum sine omega t and I maximum sine omega t. We have in the phasor form, V and I across the resistance are in phase, having the same angle, which is equal to 0. Then we have the waveforms of the voltage and the current are beginning at the same angle and ending at the same angle. Then they are in phase. They begin and end at the same angles over time. For a purely resistive element, the voltage across and the current through the element are in phase, having the same phase angle with their peak values related by Ohm's law. The relation between I maximum and V maximum is Ohm's law. V maximum equals I maximum times R. For the inductor, we have the voltage across the inductor equals L di L by dt. If L equals I maximum sine omega t, then we take the derivative of the sine, which is equal to the cosine, and the derivative of the angle omega t with respect to time will be omega, and then we multiply by L, and I maximum is multiplied by these values. L omega I maximum is the V maximum, or the maximum value of the voltage, and we can substitute cosine omega t by sine omega t plus 90. Then we have a phase shift between the voltage and the current equals 90 degrees. The quantity omega L, which is multiplied by I maximum, is called the inductive reactance, or the reactance of the inductor to the passage of current across it. From the word reaction of an inductor, it's a reaction of inductor of the passage of current and the application of voltage. Is symbolic, or it's having the symbol of XL, and is measured in ohms. It has the same measurement, or the same unit of resistance. We have the current having an angle equal 0 and the voltage having an angle equal 90. Then there is a 90 degree between the voltage and the current. They are out of phase by 90 degrees, or the current lags the voltage by 90 degrees, as we have the waveform. The waveform of the current is beginning at 0, and the waveform of the voltage is beginning at negative 90. Then the voltage leads the current by 90 degrees, or the current lags the voltage by 90 degrees. For the value of the inductive reactance, or XL, which is equal to omega L, which is the V maximum over I maximum, as the Ohm's law for the resistance. The third element, which is the capacitor. For the capacitor, we have IC equal to C dV by dt, C and the derivative by dt of V, which is equal to V maximum sine omega t. We have the derivative of the sine equals cosine, and the derivative of the angle, which is equal to omega, then multiplied by C and V maximum to complete the term. We have C omega V maximum will be the maximum value of the current. Then we have I maximum, and the cosine omega t is substituted by sine omega t plus 90. Then we have the current is leading the voltage by 90 degrees. The quantity, which is equal to 1 over omega c if we divide V maximum by I maximum, is called the capacitive reactance and having the symbol of XC and is measured also in ohm like the XL. XC equals 1 over omega c, which is equal to V maximum divided by I maximum and is measured in ohms also. For the current in the capacitor is having an angle omega t plus 90, and for the angle of the voltage, which is having an angle of 0, then the current in the capacitor leads the voltage. The current here is beginning at negative 90 and the voltage is beginning at 0. Then the current leads the voltage by the 90 degrees. Then I leads V by 90 degrees for the capacitor. For an ideal resistor, we can assume that the frequency will have absolutely no effect on the impedance level, as the resistance is not affected by the frequency. If we have a resistance equal to 22 ohms and the frequency of the source is varying from 0 to 20 kilohertz, then the resistance will remain the same, as the value of the resistance does not depend on the frequency of the source. For the inductor, XL equals omega L and omega equals 2 pi FL, then the inductor or the inductive reactance is directly proportional to the frequency. As the frequency increases, the inductance or the inductive reactance increases. If we have frequency equals 0, then XL equals 0, short circuit, and for a very high frequency value, almost infinity, then the XL value will be equal to infinity or open circuit. Then the XL value is varying with the frequency as a linear relation, as they are directly proportional. For the capacitor, XC equals 1 over omega c or 1 over 2 pi fc. Then XC is inversely proportional with the frequency. Then at low frequencies, frequency equals 0, then the capacitor is equivalent to an open circuit, or the capacitive reactance is equal to 0. And for very high frequencies, then we have the capacitor will be equivalent to a short circuit, as the XC is inversely proportional with the frequency. At low frequencies, XC is a very high value, and at very high values of frequency, XC will be almost 0 for an infinite frequency. Average power and power factor. To get the instantaneous power, we multiply the waveform of the voltage by the waveform of the current. Then we get the waveform of the power, which will be always positive. As for the voltage and current negative, we multiply by each other, then we get a positive power. We can get the average for this power, which is equal to V times I. For an inductor, a pure inductive element, we have the current and the voltage. The current lags the voltage by 90 degrees. Here we have positive voltage and positive current, then the power is positive, and for the part after it, the current is positive and the voltage is negative, then we have a negative power. After that, we have negative current and negative voltage, we get positive power by multiplication, and for the next part, the voltage is positive and the current is negative, we get a negative power. If we get the average for this power, we will see that the positive area equals to the negative area, then the average power equals 0. Also for the capacitor, where the current leads the voltage by 90 degrees, here the current is positive and the voltage is negative, then the power is negative. After it, the current is positive and the voltage is positive, then the power is positive. And after it, voltage is positive and the current is negative, then the power, the multiplication will be negative. Then the current is negative and the voltage is negative, then the multiplication is positive. We have the average value for this power also equals to 0, as the positive area equals to the negative area. Then for pure capacitive element and the pure inductive element, the average power will be equal to 0. Only the average power is present, or we have an average power in the case of pure resistive element. For purely resistive AC circuit, the average power P is given by V times I, or I square R, or V square over R, where V and I are the RMS values for the voltage and current. For RLC series circuit, we have a term called impedance. The impedance, which is equal to the square root of the real part, which is the resistance square. And for the imaginary part, XL and XC, we take XL with positive sign and XC with negative sign. We take the equivalent of these two reactances, which is XL minus XC all squared. And for the angle, tan phi, which is equal to the imaginary part, which is XL minus XC divided by R. We have the current and the voltage in the resistance in phase. For the voltage in the coil leads the current by 90 degrees, and the voltage in the capacitor lags the current by 90 degrees. For the impedance, we have the real part, which is R, and the imaginary part, which is equal to XL minus XC, or the difference of X. Then the equivalent or the resultant, which is the impedance Z, having the magnitude or square root of the real part, which is R square, and the imaginary part, XL minus XC all square, and the angle phi equals the tan phi equals the opposite divided by the adjacent, which is XL minus XC divided by R, where when XL is bigger than XC. If we have XC bigger than XL, then the triangle will be in the negative imaginary part. XC is bigger than XL, and for the real part is R, and the impedance will be in the opposite or mirror of the first impedance diagram, and this is the angle alpha. Alternating current analysis, the power is the average power. We have for a resistance, the power is a multiplication of the current and the voltage, which is always positive for the positive half cycle, and for negative current and voltage also it is positive. We have the apparent power S equal V times I, V maximum sine omega t times I maximum sine omega t, which is equal to half V maximum I maximum, the multiplication of sine, which is sine square, equals half 1 minus cosine double L angle. And for the reactive power is equal to 0. This is the power in a reactive element. We have two types of power, the real power or the average power, the apparent power, which is called S, apparent power, and 4Q, which is the reactive power. For an inductive element, we have S equals V times I, V maximum sine omega t plus 90 times I maximum sine omega t. We have half V maximum I maximum sine double the angle. And for the real power equals 0, as the positive area equals the negative area, then the average power will be 0. For a capacitive element, or only capacitive element, purely capacitive element, S equals V times I, V maximum sine omega t minus pi over 2, I maximum sine omega t. We get S equals Q equals negative half V maximum I maximum sine 2 omega t, which is sine double of the angle. And for the P, the real power, which is equal to 0, as the negative area equals to the positive area. DC power calculations, power equals V times I, or I square R, or V square over R. And for the AC, we have three types of power: the active power or the average power, which is the power in resistances, which is equal to V times I times cosine phi, which is measured in watts. And for the second form of power is the reactive power, which is present in a reactive element XL over XC, which is equal to V times I times sine phi, and is measured in volt ampere reactive. Volt ampere, the units of volt and the current, volt ampere, reactive as it is in is happening or is present in reactive elements. The total or the resultant of these two powers is the apparent power, which is equal to V times I and is measured in volt ampere, and is used for rating many devices in electrical systems. For the impedance, we have Z equals R, which is the real part, plus J, which is imaginary number of root negative 1 times X, X is the reactance. If we multiply Z by I square, or we have V square over Z, then we get the apparent power S. And if we multiply R by I square or V square over R, we get the real power in the resistance. And for I square times X or V square over X, we get the reactive power in the reactive element. For the power triangle, which shows the relationship between the real power, reactive power, and apparent power, we have the real power, which is in the resistances and is horizontal. Perpendicular to it is the reactive power, which is positive for inductance and negative for capacitance. And the total or the resultant power, which is the apparent power S equals from the triangle the square root of p squared plus q squared from Pythagoras. And for the complex form of S complex equal P plus JQL, where S equals V times I in volt ampere. If we analyze S in the horizontal axis, we get P, which is S cosine theta. And if we analyze it in the vertical direction, we get Q, which is S sine theta in volt ampere active, and for the real power in watts, and the apparent power S in volt ampere. Now we will see an example. A coil of resistance 5 ohm and inductance 120 millihenry series connected in series with a capacitor of 100 microfarads and across a 300 volt 50 hertz supply. The current flowing is the first required, and the phase difference between the supply voltage and the current is the second required. The voltage across the coil, third required, and the fourth required, and the last one is the voltage across the capacitor. First of all, we get the reactive element reactance. XL equals 2 times pi F L, 2 times pi F equals 50, and L equals 120 milli. Then times 10 power negative 3, we get XL equals 37.7 ohm. Therefore, XC equals 1 over 2 pi FC, 1 over 2 pi times 50 times C 100 times 10 power negative 6. We get XC equals 31.8 ohm. We get the total X, which is XL minus XC. XL equals 37.7 and XC 31.83. We get 37.7 minus 31.83, which is 5.87 ohm. For the Z, which is the square root of R square plus XL minus XC square, we get the root of 5 square plus 5.87 square, which is equal to 7.71 ohms. For the current, we get the magnitude of the voltage divided by the impedance, 300 divided by 7.71, we get the current equal 38.91, which is the first required. For the phase difference between the supply voltage and the current, we get the angle of the impedance, which is tan inverse the difference of XL minus XC divided by R, which is tan inverse 5.87 divided by 5, which is 49.58 degrees, and this is the second required. We need to get the voltage across the coil. Then we get the impedance of the coil ZL, which is square root of R squared plus XL squared, which is 38.03. We multiply I by times ZL, 38.91 ampere times 38.03 ohm. We get 1480 voltage. For the phase angle of the coil, we have 10 phi equals tan inverse XL divided by R, tan inverse 37.7 divided by 5, which is 82.45 degrees. And for the capacitor element, we get the voltage across the capacitor, which is the last required, which is equal to I times ZC, I equal 38.91, and ZC, which is equal to the value of the XC, 31.87, or negative JXC. If we have the angle, then it will be 1239 voltage. In the next lecture, we will discuss the power factor, series and parallel AC circuits, and the three-phase circuits. See you all in the next lecture. Goodbye.